Good morning. I'm starting the week 2 lecture on heat exchanger. So first part of this week 2, I have discussed about different modes of heat transfer like conduction, conduction, convection and radiation. And we discussed about electrical analogy and we calculated some numerical problem. Now this lecture will contain basically heat exchanger which is used on your shipping machineries or other applications. In shipping machinery, where do you apply this heat exchangers? You have refrigeration system, or you have air conditioning system, you have boiler system, you have IC, internal combustion engine, or you have other type of engine, okay, other type of engines, or you may have heat recovery unit. So many places you have heat exchangers. So what are the heat exchangers? What is the definition? How to calculate? How to size it? So that sort of calculation we'll do in this lecture. So in this picture, you can see this black picture. I have shown here. That black line is going like this, and it is going like this going out. Okay. So this is called tube. Okay, through tube maybe hot fluid is going, and if it is tube and hot fluid is going inside, surrounding temperature, air temperature may be 25-30 degrees centigrade temperature, and so in heat from the tube or pipe will be going out to the atmosphere. Okay, now if I have very small tube, then you can remember the convective heat transfer coefficient, heat transfer rate, HA del T. So area, surface area smaller means your heat transfer rate will be smaller. Now how to increase the surface area? Actually you are creating multiple pass tube, long tube, you are making serpentile. So your total area increasing because pi d, the diameter, into L. Okay, so L increasing. So when you are increasing L, your diameter increasing. When diameter, your length increasing, when you're increasing length, your area increasing means your heat transfer rate also increasing. And convective heat transfer rate, let's assume this is natural convection, there is no fan or anything. If you have fan, then heat transfer rate will be further increasing. Another option is that whether can you increase del T, temperature difference. If you can increase, then heat transfer rate also will be higher. So we'll discuss how to do it. Okay, then what is heat exchanger? Heat exchanger is a piece of equipment built for efficient heat transfer from one medium to another. Okay, so one medium is, this is your hot fluid, maybe T high, T low outside temperature, or T cold. So heat will be getting transferred through the pipe. Okay, this is called heat exchanger. So a heat exchanger is a piece of equipment built for efficient heat transfer for one medium to another medium. The medium may be separated by solid wall so that they can never mix, or they may be direct also. For example, some fluid can mix and it can transfer heat from one fluid to another fluid, or it can have solid wall. Normally there will be on solid wall so that hot fluid and cold fluid will not mix, because hot fluid may have some different property, cold fluid will have different property. For example, oil and water, or water going through pipe and outside air. So you cannot mix air and water, right? So you must have on solid wall. So through wall heat transfer will be happening. So wall means the tube. So tube material, already we discussed, normally it will be copper. Okay, normally copper will be a tube material, and if you are using other material, for example iron, then heat transfer rate will be lower. Aluminum also you can be you can use, but you cannot use gold or silver, although they are having very high heat transfer rate or conductive heat transfer coefficient. So example I have shown already, this refrigeration, air conditioning, boiler, IC engine, other type of engines. Many applications are there on your shipping machinery or in your day-to-day life also. So previous lecture I was giving one example of chula, that Indian household they will be using oven, right? And fuel or wood or coal will be given, and burning or combustion will be happening. So there will be combustion. or chemical reaction. Okay, combustion or chemical reaction will be happening. So because of chemical reaction, lots of exothermic reaction will be happening. This is called exothermic. Exothermic reaction will be happening. Because of exothermic reaction, you will get lots of heat. So heat will be whatever wood or coal you are giving from the hole, so their air also will be coming in. Okay, after burning, it will create lots of hot gas. So hot gas will be coming through this one. It will be hot gas, and sometimes we say flame. Flame means actually it will be hot gas very high at very high temperature. So if you have lots of carbon particle, so carbon particle at high temperature, it will be like yellow color. But if there is complete combustion, if something is burning completely, so in that case you cannot see the flame. Actually bluish or yellowish, bluish color you can see. For example, you have oven at your home, Indian gas ovens, so they are designed properly. So all the gas whatever you are giving through your Indian cylinder, so that cylinder, that gas will be burning completely. When burning completely, there is no carbon particle, so you will not find yellowish flame. But if yellowish flame is coming, that means there are lots of unburned hydrocarbon or carbon particles are there, or maybe carbon monoxide also getting produced because of low amount of high oxygen supply. If you supply proper amount of oxygen, then combustion will be proper. Then you will not see the yellow color flame. Okay, only you will see hot gas coming out from your oven. Okay, now hot gas will be transferring heat to your pot. Okay, this pot may have water, so heat is getting transferred through this metal metal pot. Okay, so this is also heat exchanger, exchanging heat from air to water. Okay, so this is also one example of heat exchanger. Normally you have seen in rural households in India, or even in your city, there will be Indian cooker and in that oven. So there also heat will be transferred from air to pot, then water, and water you will have any vegetable or meat or any other stuff, so that will be getting boiled. So heat exchanger types. There will be several types of heat exchanger, but most common type is shell and tube type. Shell and tube heat exchanger. Instead of total heat exchanger term, I am writing HE, heat exchanger. Okay, shell and tube heat exchanger. Another will be plate heat exchanger. Another can be air cooled heat exchanger. Air cooled heat exchanger. In shell and tube heat exchanger, the most common type of heat exchanger. So these are used in oil refineries and many other applications also there. In shipping machinery also you can use shell and tube type heat exchanger. This is very compact type heat exchanger. It is being used in the industries. This type of heat exchanger consists of shell, a large pressure vessel, and with a bundle of tube inside. So here you can see this right side picture. This is a pressure vessel. Okay, this is a large pressure vessel, maybe high pressure vessel, and there will be one inlet, one exit. Okay, so here, for example, if this is inlet, this is exit, this is inlet, this is exit. So one fluid will be entering, it is going through this, then it is going through this blue color, you can see, and it is going out. Okay, this is inlet, this is outlet, and this is another fluid 2, maybe fluid 2. Okay, so fluid 2 inlet, this is exit or outlet. Okay, and what is happening, fluid 2 is coming and it is going to the shell or the vessel, and another fluid which is fluid 2 is coming and it will go through pipes. Okay, small pipes will be there. So one fluid is going through the shell another fluid is going through the pipe, and both fluid are not mixing, but they are exchanging heat, and there will be pipe will be multiple time going from left side to right side, or maybe one time. One time means the pipe length is shorter, so heat transfer rate will be lower. So they will be having multi-pass or multiple pipes going from left to right, okay, left to right, right to left, right to right. So that way it is increasing the total surface area or length of the pipe. When total length of the pipe increased, Q is increased. Already I told the formula, Q equals HA del T. Okay, so you are increasing actually A means pi d L, D means diameter of the pipe or duct, and L is length of the pipe, PIPE. Okay, and plate heat exchanger, another type of plate heat exchanger is there. So especially in western country, during winter season they will be using plate heat exchanger for room heating purpose. How? Through these plates will have a hot pipe, okay, it will be like this. Okay, this one pipe will be entering here, it will be going like this, then another plate going like this, another plate will be. So what will happen when hot pipe, this hot gas is going through the pipe and it is connected to plate. So the pipe will be transferring heat to the plate, okay, one plate, two plate, three plate, four plate, five plates, and pipe is like this, okay. So pipe is transferring heat, so pipe will be quickly transferring heat to the plate, and any air nearby the plate will be heated up. So for room heating purpose, people are using in western countries this type of plate heat exchanger. This is actually shell and heat, okay, this is plate heat exchanger. Okay, another type is air cooled heat exchanger, simply pressure vessel which cools a circulating fluid with fin tube. So fin tube means one tube is here, okay, and let's say hot gas is there, hot fluid and cold fluid. Hot fluid is going through this pipe and cold fluid around, and to increase heat transfer rate you put lots of metal extrusion like this. Okay, what will happen, the pipe temperature, let's say 100 degree centigrade, so this fin temperature also will be 100 degree centigrade. Okay, so fin should not be too long, it will be having some optimal length. Okay, if fin temperature would be maintained almost 100 degree centigrade, because from surface to this end, okay, surface to this end, okay, this is also 100 degree, this is also 100 degree centigrade. Now what happened, so because fin extended, that means you increase surface area, okay, you increase the surface area, you see I am making dots here, okay. So increase this surface area, initially surface area was like this, now my surface area become like this, so you get extra this surface, I am putting hash line, okay, this extra hash line, this area extra surface you got. So extra surface you got means HA delta T, your A increased, initially if it was HA delta T, now it become HA plus A dash maybe delta T, okay, because you increase surface area, your heat transfer rate will be increasing. Okay. In many cases this extended surface or finned surface will be used, for example, I'll give example later. For example, motorcycle engine cooling or your cycle compressor cooling in your hostels, there will be cycle compressor, you can see there will be heat exchanger system, there will be heat exchanger in your motorbikes or shipping machineries, there will be lots of application, even in computer also there will be heat sink or this protrusion surface or that micro channel they say. So they are also having this finned or extended surface to increase heat transfer rate. So single pass and multiple double pipe flow arrangement. Single pass means like here you can, in this picture you can see multiple pass. Okay, one pipe is coming here, it is going like this, again going like this, going like this. So it is creating multi-pass, a double tube heat exchanger, multi-pass. Okay, multi-pass means multiple time if pipe, so pipe will be longer, but single pass means pipe will be shorter. Another case, double pipe. Double pipe is like this. I have one pipe over another pipe. Okay, so I'll draw this picture. You also can draw if you like. This is inner pipe, this is outer pipe. Okay, inner pipe, I'm just making some dots over it so that you can identify separately. Okay, this is outer pipe, outer pipe, this is inner pipe. Okay, and outer pipe, inner pipe, fluid flow direction can be same or different. Like say one fluid is going through this, fluid 1, this is maybe fluid 2. Okay, so fluid 2 going through, coming out also, fluid 2 in, this is out, this is fluid 1 in and fluid 2 out. Okay, and it is also possible that fluid 1 and fluid 2 direction can be opposite. How? Okay, so I have another pipe, let's say like this. Okay, one pipe flow direction this, another pipe flow direction this. Okay, so you see this flow direction also can be opposite. So the same direction flow can be applied for your case, or opposite direction flow can be applied for this. For that we will do some calculations later. So air cooled heat exchanger, actually air cooled heat exchanger. Air cooled heat exchanger, you may have seen, if big buildings are there and air conditioned building, for example big shopping malls, there will be centralized air conditioner. So outside the building there will be certain pipe, you can see lots of pipes will be there. Okay, and lots of water will be splashed over it. You may have noticed in cold storage system also, outside cold storage building there will be such system, and lots of water will be splashed. Okay, what they do, they'll be having this metal pipe. Okay, if you need stronger pipe, normally steel pipe also you can use, but copper pipe is little bit softer, or strength wise steel pipe is stronger. So hot fluid, or the hot fluid coming from a refrigeration system or air conditioning system through this pipe. Okay, and you have to cool down quickly. So you have longer pipe, serpentine pipe, and to cool down this one you can splash water. So the water will be, when touching this surface, water will take lots of heat. If temperature is very high, then water will get evaporated also. When it is getting evaporated, already we discussed that evaporation means it will take some hidden heat, latent heat, so it will be cooling down quickly. Okay, so that system also will be there. And some, because it is open to atmosphere, so air also will take lots of heat, so water will get splashed, some water will get evaporated, some water get higher temperature, the atmospheric surrounding air also will get heated up, and because of it is in atmosphere, that hot fluid or hot air and water will go out and your pipe will be cooled down quickly. Okay, hot, cold, hot fluid from your heating, ventilation, air conditioning. We say heating, ventilation, and air conditioning. Heating, ventilation, air conditioning, condenser, actually this is actually condenser. Okay, so heating, ventilation, like, or if you see your simple domestic air conditioner or refrigerator system, if you go to back side of the refrigerator, you can see certain pipe like this. Okay, if you go to back side of your air conditioning system, there will be certain pipe like this. Okay, so that is actually condenser. So that heat from your room will be removed and it will be sent out to outside, right? So outside heat means it will go through this condenser. So that's why the condenser should be placed outside your house, and there it will be interacting with normal atmospheric atmosphere or air, will be taking up lots of heat from this one. Okay, but if you have big buildings, shopping malls, then the narrow pipe used for your domestic refrigeration system or air conditioning system, that pipe will not be used. So this will be bigger pipe. This is wider pipe, maybe 1 or 2 inch or 3 inch, 4 inch diameter pipe will be there. For example, big shopping mall in Chennai, if you see this Phoenix Mall or any malls, so they will have also this sort of thing, because they will be having centrally air conditioned system. Heat exchanger classification. So heat exchanger classification, one is regenerator heat exchanger will be there. Regenerator heat exchanger means like lots of waste heat will be there. So whether can you get some recuperator. Okay, these are actually heat recovery unit, like say IC engine or other engine, it will be producing lots of heat. IC engine or gas turbine engine or any type of engine or boiler system, when you are burning certain fuel burning means combustion happening, exothermic reaction, lots of heat is getting produced, you are using certain amount of heat, but 100% heat you cannot use. For example, IC engine efficiency will be 30 to 35%, so 70% heat will be wasted. Okay, when 70% heat is being wasted, whether can you use that one? So there are some mechanism to use that waste heat to produce steam or for other hot water creation or some other purpose you can use. So there also you are using heat exchanger. Directly you do not put water into your cylinder, piston, engine or gas turbine system. Okay, exhaust gas you are getting, so the exhaust gas will be used for certain practical purpose, okay, to increase your system performance, so that whole shipping machinery fuel cost will be reduced. On ship, whatever work you do, for example heating your water, pumping water, cleaning deck or anything, energy is required. Energy means in terms of fuel you will be taking from somewhere. Okay, these is battery operated systems are coming. Battery means again somewhere fuel is getting burned or some renewable energy source are used to charge battery. Okay, so energy is required everywhere. Okay, so energy required, again second law of thermodynamics says that energy will be lost every time when you are transporting from one point to another point, or converting from mechanical to electrical to mechanical or any other form. Okay, so there will be every time there will be losses, and final form of energy is heat. So if you can capture that lost heat by some mechanism, so that will be beneficial for you. So lots of engineers and scientists, they are thinking how to reuse the excess or waste heat using some heat exchanger mechanism. Okay, already being used, but still people are doing research, so that design optimization, compact system, efficient system they are trying to make, and they are trying to include the solar system, battery operated system, hybrid energy system. For example, whether ethanol and diesel can be mixed, or hybrid engine, maybe solar some energy, maybe some oil based energy, maybe some battery also. If you can put, then maybe it will be more energy efficient and it will be towards sustainable goal. Now you can see this United Nations has created sustainable development goals, several goals they have selected, and goals are that how to make the human being the life better for human being. Okay, so there will be like single phase heat transfer system. Single phase system is like water or gas is going, so outside also water, okay, or outside maybe gas, so phase not changing. Another case maybe there inside one fluid is going very high hot fluid, for example boiler, hot gas is there. In boiler what happens, you burn fuel, then you are getting lots of heat, or you got any excess heat from some machine, and that will be used to boil some water, and that boiled water will be used for some other purpose. So in two phase is happening, so that will be evaporation possible. In some cases you do condensation. Condensation means inside your refrigeration system, the condenser, I said the condenser for refrigerator, air conditioning system or cold storage system, the condenser part actually it will be the pipe will have initial entry will be hot gas, hot steam or gas. So after cooling here it will be creating liquid. Okay, so hot water you are giving, liquid water you are getting out. getting here. So phase change is occurring. Okay, in some cases evaporation will be occurring. For example, refrigeration system, you have evaporator. Okay, in refrigerator system, I'll draw one refrigerator system actually. Condenser, from condenser it will go to cooling. After cooling there will be throttle valve, pumping system, compressor, then evaporator, and then throttle valve. Okay, so in refrigeration system what happens, in evaporator system it will be there inside your fridge. Okay, and condenser will be outside of your fridge. So inside your fridge evaporator, it will evaporate lots of refrigerant, and this whole flow loop will have refrigerant. Okay, refrigerant or liquid, let's say CFC and all, and ammonia or chlorofluorocarbon or other type of refrigerant will be there. So those will be circulating through this loop. Okay, and evaporator will be the inside refrigerator. So evaporator means liquid you have and you are evaporating. When it is evaporating, it will take lots of heat. So from where the heat will come, it will come from your vegetable, fruit, meat, milk, whatever they are inside fridge. From there it will take heat and it will evaporate from liquid to steam or gas it will produce. So that gas will be sucked by compressor. Okay, then it will be compressing again. When it is evaporating, it will be increasing volume. Okay, liquid volume low, evaporation, after evaporation volume will be higher. So one compressor will be there. So compressor will be compressing it again. When it is compressing, again you go to Charles law. Compression means it will generate lots of heat. So high temperature, high pressure fluid will be getting here. H high, temperature high, pressure high. Okay, high temperature, high pressure fluid you get after compressor. So that high temperature, high pressure fluid you pass through condenser. Okay, so condenser will be releasing lots of heat. When it is released lots of heat, so that high temperature, high pressure gas. Okay, now it will be liquid. Okay, temperature will be low, low temperature, pressure also low. Okay, low temperature, low pressure created after condenser. So that low temperature pressure fluid will be passing through your throttle valve. Low temperature, not pressure. Pressure will be here. Low pressure. Okay, after throttle valve is very narrow restriction you create, and slowly you pass fluid through the restriction. So pressure will be lower after throttle valve, and the low pressure fluid will be going to evaporator chamber. Evaporator means inside fridge, and you are getting your system cooled. Okay, now what is happening in condenser? You have heat exchanger. Evaporator you are having heat exchanger. Condenser phase change occurring, and evaporator also phase change occurring. So in some heat exchanger phase change will be occurring. In some cases there will be no phase change. For example, gas to gas heat transfer, or maybe you have one boiler system. In boiler system you have superheated boiler you are creating. Superheated boiler, you can remember, I already told TS diagram. You are increasing temperature, you are increasing temperature further. So this area superheated area. Okay, this is inside this envelope. It will be liquid plus gas. One process will be happening, but outside envelope this area will be superheated, means completely gas. So gas is there and you are still increasing temperature from your burn gas. Burn gas means coal or oil you burn, you got very hot gas. Hot gas will be increasing your steam temperature. It is already gas, so you are increasing further temperature. So in that case single phase but temperature increasing. Okay, in some cases you are changing phase, temperature increasing or reducing, pressure increasing or reducing, that will be happening. Okay, so then single phase possible, phase change possible. Okay, in through the condenser. Then there will be other different types of heat exchanger. For example, one already I told that pipe will be there. So outside temperature something different, inside temperature something different, and you are transferring heat. Another will be plate heat exchanger. Okay, so we have one multiple plates, 1 2 3 4 5 6. So plate temperature something different, and in between the space between the plate, the temperature or another fluid will be there, so the temperature will be different. So plate and that fluid heat exchange will be happening. And another option is that I told enhanced surface or extended surface we create, and we try to create heat transfer rate, try to increase heat transfer rate. Okay, for example, if this is your surface, so it will be increasing heat transfer rate. But initially, let's say this one your original surface, this is modified surface. So modified surface, okay, so modified surface will have higher heat transfer rate because it is having some extended surface that will be giving more surface area, HA, Q equals HA del T. So more surface area means more heat transfer rate. Okay, another will be I already told that same direction flow, they call parallel flow. Like say I have two pipes. Okay, one pipe is here, another pipe is here. Okay, so same direction flow, this is called parallel flow. But if flow direction different, okay, so outside pipe flow direction this, inside pipe flow direction opposite, so this is called counter flow. Okay, another flow or situation will be like cross flow. Cross flow means, like say two plates are there or two pipes going, let's say this direction, but another fluid is going just perpendicular to the flow, so that will be cross flow. So the figure I can draw like this, parallel flow, cross flow, like this. I have another flow will be like this. Okay, so one fluid is going, another fluid is going, like A, B, B. So B entering, B exiting, A entering, exiting. So there may not be mixing, but their flow direction is cross. Okay, so two things I have shown, parallel flow, counter flow. Those are parallel flow, but cross flow, this is called cross flow. So different arrangement of heat exchanger also possible. Exchanger surface will be there, phase change will be there, parallel flow will be there, cross flow. So different combination of heat exchanger they have designed just to optimize space, maybe cost, maybe heat transfer rate. Okay, so concentric tube. Okay, when you are designing concentric tube heat exchanger, so heat exchanger can be looking like this. Okay, inside fin will be there. Okay, in some cases, so you can draw completely. But in some cases, the heat exchanger can be looking like this. Pipe outside, lots of fins will be there, so that you are increasing surface area. Okay, you are increasing surface area and you are increasing heat transfer rate. So this is internal fin, this is external fin. Okay, and this pipe arrangement inside your heat exchanger also may be different. For example, this may be one piping arrangement, central one like this. Okay, so how to optimize it? So inside pipe, when fluid is flowing, you are trying to create turbulence. So that turbulence means more mixing, more heat transfer rate. So how to create turbulence? Two pipes are there, and if they are creating laminar flow, one layer, let's say one plate, another plate is there, and you are creating very slow laminar flow. What will happen? Laminar flow means one sublayer, viscous sublayer will be there, another viscous sublayer will be there. So some fluid particle will not touch the metal surface. Okay, because it's laminar flow, very slowly, smoothly it is going through this one. So some fluid will not get enough heat to get heated up, But if you are creating very high velocity means lots of turbulence will be created in between these plates or any surface is there. So when turbulence is there, particle will be moving, okay, it will be mixing with hot particle, cold particle. When mixing up happening, so more heat transfer will be happening, okay. So your intention will be to increase turbulence, to increase heat transfer rate, so to increase heat transfer surface area. So to increase H, when you want to increase H, you are increasing surface area, turbulence, okay, or you increase A using your extended surface of fin, or in some cases possible increase del T also, okay. So three parameter you have for heat transfer increasing: H, A, delta T. So any of this or all of this you can modify so that you can make a compact heat exchanger. In many places you will not have enough space to put all these things together. For example, in submarine you are designing, so your space is very limited and you have to do heat transfer properly, okay. So then all the parameters you have to consider. Okay, now I have one shell and tube heat exchanger. Okay, let's say I have one shell and I have lots of tubes, one tube, okay, two tube, three tube is going through the shell, okay, and flow direction like this, and this fluid is going, maybe this is hot fluid, this is cold, okay. So you are trying to reduce hot fluid temperature, okay. What happens if you have hot fluid going through the pipe and cold fluid is crossing these pipes, it will reduce heat, but if you make some more arrangement to create turbulence, so what you do, you have pipes, okay, uh, one pipe, two pipe, and you have, this is your shell maybe. Now create one baffle, okay. So what will happen, when fluid will be entering here, it will go, it will turn, again it will go, it will turn, it will enter, it will go, it will turn, and it will enter. You can create multiple baffles also. So your more, the cold fluid will have more turning means more turbulence you are creating inside, more turbulence and more mixing you are creating, so more heat transfer will be created. So different types of baffles you can arrange, and baffle will not be covering whole area. For example, if you see this one, top one, so baffle, like I have one exchanger and only some portion will be covered, okay, not completely. So that fluid will be entering, again turning down, again up, again turning down, again up, it will be happening, okay. So it will be having lots of drill hole, through the drilled hole pipes will be entering. So one pipe will be entering through this, and another baffle will be there. So maybe one pipe will be entering and this will be entering to baffle and it will go out, okay. So that way you are getting more turbulence, okay. Now pipe arrangement also, there will be several types of arrangement. For example, if you see square pitch, triangular pitch, so different types of piping arrangement will be there. So one shell is here, so one pipe, two pipe, how to put the pipe so that more heat transfer rate will be there. So there will be different lays, square pitch sort of thing, triangular, many other types also there. So I have given two example for this one. So this picture actually I have taken from oil and gas related book, okay. So but heat exchanger is common for all aspects, all the applications, okay. I already said that heat transfer you have to increase so that you can make compact heat exchanger, okay. And when you are trying to create compact heat exchanger, I was working during my PhD for dimple channel heat exchanger. What is this dimple channel? Like I have one flow channel, okay, and you have hot fluid is let's say this is heated up, pipe is heated, this is cold, okay, and you increase the cold water temperature or fluid temperature to high, okay. Then now if you have only simple channel, then fluid will be creating one boundary layer, okay, and central fluid will be going like this. So this boundary layer, this nearby wall some fluid will not touch, because near wall the fluid velocity will be very low, and that fluid particle will not try to move slowly. So, that will create actually some laminar flow, and natural convection will be holding. So, there will be no turbulence effect. So, to increase heat transfer, what I did, I put some cavity on the surface. Okay, let's say protrusion or cavity. This is protrusion, this is cavity, or dimpled. It's a dimple channel. So, you can see lots of dimple will be there on cheeks, right? So, the dimple channel we created. So, what happens when fluid is creating laminar flow, suddenly it will face this cavity, then it will create loss of turbulence. Okay, and here also it will get some stopper, okay, or it will get some resistance. So, again it will create loss of turbulence. So, fluid will not create laminar flow, rather it will break this turbulence boundary layer or laminar sublayer, and it will create lots of turbulence. When turbulence will be happening, lots of flow mixing will be happening. Okay, when flow mixing happening, your heat transfer rate will be increasing. So, if you have any channel, you create some dimple or protrusion or certain arrangement, so that you can create more turbulence. Okay, more turbulence you are creating means more heat transfer will be happening. But if you are increasing too much turbulence, that is also very good, but problem is that when turbulence is created, your pressure drop, frictional pressure drop will be increasing. So, let us say you have one pump is working to deliver fluid through the channel or pipe, and you have created lots of turbulence. So, pump will be requiring more power, electrical power, to push the fluid through this one, because you have lots of turbulence, lots of resistance. Smooth path, you have smooth path. The smooth path will have less resistance. Fluid will be happy to go from one end to another end. But if you have lots of resistance, you are creating turbulence, but it will take lots of energy from pump, because the fluid will ask pump, hey, give me more energy, otherwise I cannot move. Okay, so frictional pressure drop will be increasing. So, my work was actually to optimize what will be the optimal size. For example, initially I took the upper picture, flow direction, you can see this is the flow direction, and lower picture actually my optimal shape I got. Okay, the shape becomes smaller, so that I got fluid flow like this. No, not like this. It went there, then lots of turbulence created, again lots of turbulence created, again when it is exiting, again it is getting another cavity, it is getting another cavity. So, lots of turbulence are being created, and channel is like this. This can be both dimpled or one dimple, one protrusion. So, I have shown here, and the channels on the both surface, two surfaces are there. So, dimple can be different way we can arrange. For example, dimple can be here, 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 here randomly, or there will be certain pattern. So, what will be the optimal pattern? What will be the optimal cavity size? What will be the dimple shape? How many dimples should we place? So, that sort of optimization I have done. So, main purpose was to increase flow mixing and turbulence, and to reduce pressure drop or pumping power requirement. So, that was my objective. So, if to know more about this one, you can go through my paper, multi-objective optimization of dimple channel heat transfer.